Hi, my name is Catherine Amstutz, and this is my experiment 3 lab report. The purpose of this experiment is to predict the behavior of circuits with resistors in series and in parallel, to measure the actual conventional current and potential difference values within a circuit, and to determine the RC value of a circuit based on experimental and calculated data. The results in part 1 were that current 1 is equal to current 2, which is equal to 0.02 amps, which matched my predicted value. And for part 2, the RC experimental was 5.9988. Also very close to my experimental value of 6. Some fundamental physics principles that will be important for this experiment are Ohm's law, which is that delta V for any circuit element is equal to the current times the resistance, and then Kirchhoff's loop and node rules. So the loop rule is that due to path independence, delta V is equal to 0 across a loop. So if you could draw a loop around it, you can say that the total change in voltage is going to be 0. And then the node rule says that the sum of the currents entering a node is equal to the sum of the currents leaving said node. Over here, we have some equations. So this starts off with a version of the loop rule, and then through taking some derivatives and some linearization, we find that the natural log of the relationship between the change in voltage over the initial change in voltage of a discharging capacitor is equal to negative t, the time after the capacitor began discharging, divided by RC, and this is what we'll use to calculate our experimental RC value. This is still an experiment, even though it's all virtual. The system is the circuit, and the surroundings is everything else. The earth, the person conducting this imaginary experiment, etc. Theory, part 1. So the initial conditions for this are two 1.5 volt batteries and two resistors in series. These two ammeters are measuring current, and I predicted that because there's circuits in series, the currents are going to be identical, and use the loop rule to find that I1 is equal to I2 is equal to 0.02041. So simulation was not as decimal heavy as I was, but the value I came up with matches my prediction. And when I inserted one of the ammeters backwards, both of them still read 0.02 amps. So the reading on the voltmeter is 3 volts, equivalent to the EMF of this battery, and that's because the current can run through the ammeter, but it can't run through the voltmeter. The voltmeter essentially acts as an open switch on this circuit, and that's why the current here is 0. So I found the change in voltage across each part of this circuit, and I found the results are here. The sum of all the potential differences should be 0 to their path independence, and then they are. The addition of the voltmeter doesn't change the reading on the ammeter, which stays at a constant 0.2 amps, because very little current flows through the voltmeter as opposed to a wire or the ammeter itself. If an ammeter is connected in parallel with a 100 ohm resistor, the current running through both ammeters is 0.06 amps as opposed to the initial 0.02 amps. This is because the delta V remains constant, but the ammeter has a resistance of 0 rather than a resistance of 100, so a lot of that current, a lot of this electron is going to take the path of least resistance, which would increase the overall current of the circuit. And then here are some calculations of the different resistances of the circuit elements. RC circuits. So for part 1, as time goes on and the capacitor charges, the light bulb dims until it stops giving off light entirely, indicating that the circuit has come to a stop. So when the capacitor alone is connected to the light bulb starts out emitting a lot of light, and as it discharges, the light bulb dims and eventually stops shining altogether. While the capacitor was charging, the current was decreasing until it stopped entirely once the capacitor is fully charged, and the same happened when the capacitor is discharged. Started out strong and then decreased. It took about 6 seconds to both charge and discharge the capacitor with the 10 ohm light bulb, and it took about 10 seconds, maybe 11 seconds, to charge the capacitor and discharge it with the 20 ohm light bulb. This is the experimental data that I gathered with a circuit involving a discharging capacitor and a 30 ohm light bulb. And when I plotted the natural log of the voltage ratio against time, I came up with a very nice graph. Y was equal to negative 0.1667x plus that constant. So that 1667 is important because that's equal to negative 1 over RC, giving us this RC value here. The calculated RC value is just resistance times capacitance, or 6. The percent error is thus 0.02% error. A possible source of error was incorrect timing with the stopwatch, as I was just clicking on and off rapidly, but perhaps not rapidly enough. experiment were done in real life and used an actual ammeter, the real ammeter would have a bit of resistance. Since the current is inversely proportional to the resistance, the current in the real circuit would be less than the current in the ideal circuit. And in a real circuit, the capacitor would not reach full charge instantly, as would be predicted in an ideal circuit. That's because the model disregards resistance of the wire. In reality, the wire has some resistance, so although the capacitor would reach full charge quickly, it would not do so instantly.